Okay, let's talk biomechanics of wheels. So, a cyclist or triathlete or whoever rides bike often will need to select a wheel set for their bike, or they may have different wheel sets to choose from, and they may need to pick one for a particular course. And let's talk about why they would pick one type of wheel over another. Now, I've got all sorts of wheels here. I've got traditional wheel that you'd find on a bike. I've got a front wheel that has a little bit different shape on the rim here. We'll talk about that. I've got a rear wheel that's a little deeper rim here than the front wheel. Actually, sorry, this is a front wheel. It has a different brake structure too. We may get into that, we'll see. Let's see, I've got another rear wheel here with a particular rim depth here. It's a little different shape than the other one. It's a little wider in this area. And it's got that different type of brake on here. And then I also have a disc wheel that's solid throughout. And this would be a rear wheel too, as you can tell from the rear set of gears. Now, in order to decide which wheel to choose for a bike or for training or for a race, we've got to know something about our mechanics. There's two equations that we really need to sort of pull together here to understand what's going on. The first is sum of forces acting on the object equals mass times acceleration. And we've dealt with that. We did a kinetic analysis of cycling, and we broke the kinetics down to a propulsion force causing the bike rider to move forward. And then we identified some resistance forces. That was drag force, rolling resistance force, and slope force, those three forces. And we consider them resistance forces for the sake of discussion. Obviously, if you're going uphill, the slope force is resisting going uphill. Going downhill, that slope force would actually be a propulsion force. And we've also talked about when a drag force can actually be propelling an object forward versus resisting. But for our purpose, we're going to be considering those three forces as being resistance forces. So if we add up all the forces acting on the object, we get mass times acceleration. Mass is the mass of the system, and acceleration is rate of change of velocity. Now, when we've done this before, we've talked about velocity being constant and therefore acceleration zero. But in reality, velocity won't be constant. And we're going to get all these fluctuations in velocity as we pedal with each stroke. So if you have changes in velocity, this is linear world, you're going to have an acceleration. And the mass is the resistance to change velocity. So the more mass a wheel has, the more resistance to change linear velocity there is. And that might be helpful to have a wheel that has as little mass as possible in order to allow lots of changes in fluctuation in velocity. Again, we have these little fluctuations in velocity as we cycling. So we don't want our wheels to have a lot of mass for that reason. Now, if I'm doing some interesting cycling, I'm trying to sustain a velocity for a long period of time, then maybe I want a high mass of a wheel, because once I get that wheel going, then I can, that wheel will resist slowing down because it has more mass and more inertia. So I'm just talking about mass of the object, so just how much mass it has related to the weight of the object. All right, so that's a linear world, and that's the first equation that we need to have to understand wheel selection. And I should tell you that there's some races where we're going to see lots of changes in velocity during the race. An easy race to think about would be something that you might see in Tour de France, where there is some sprinting going on, maybe near the end of a race, where you see lots of fluctuations in velocity of the different cyclists. In that situation, you want to have as little resistance to change velocity as possible, so as little mass as possible. So you want to select a wheel set that has as little resistance to change in velocity. That's also the case for a course where you have lots of hills, a lot of climbing. Going uphill, that slope force will be a function of how much weight the object has. The weight of the object is a function of how much mass the object has. So the less mass wheels have, the less resistance to going uphill due to slope force there would be. So if I have a course that's really hilly, I want to choose the wheel set or the wheel. When I say wheel set, I mean really the combination of the front and the rear wheel. But sometimes I want to talk about one rear or the rear wheel only or the front wheel. But if I have a course that's really hilly, I'm going to choose the wheel set that has the least amount of mass as possible. And that's going to reduce the resistance to going uphill. Okay, so that is the linear equation. That's the first equation. The second equation we need to understand wheel selection is sum of torques equals I alpha. If you think back to the work that we did to understand how we transferred the force on the pedal to cause the propulsion force of the bike, we needed to know T equals I alpha, and we needed to know T equals FD perpendicular. So if you don't recall that, be sure you go back and look at the material on part 1 and part 2 in terms of how we calculated the propulsion force acting on the bike rider based upon the pedal force and using the equation sum of torques equals I alpha. So sum of torques, we know what that is. Torque is force times moment arm. I is moment of inertia, and alpha is angular acceleration. In this case, it'd be angular acceleration of the rear wheel. And that angular acceleration is going to be related to the linear acceleration as well. So just like I said, in the linear world, we said, hey, let's just deal with constant velocity, therefore we don't have acceleration. We also dealt with constant angular velocity, which means there'd be no angular acceleration. When there's no angular acceleration, that product of I, moment of inertia, and alpha drops out of that analysis. But now I actually want to bring it back into discussion, but more conceptually versus mathematically. So if we have a wheel that has lots of moment of inertia, which is a function of how the mass is distributed about the axis of rotation, it's going to have lots of resistance to change motion, meaning it's going to be hard to get it going, but once it is rotating, it's going to continue to rotate. It's going to resist slowing down. So if I have a race where there's going to be lots of fluctuation in velocity, a crit race, a Tour de France type of sprint finish, I need to be able to respond and change my velocity as fast as possible. I want a wheel that has the least moment of inertia as possible. Right? That wouldn't be this wheel. This wheel is going to have more moment of inertia. But I'm going to select this wheel if I'm going to be riding a course where I'm trying to sustain a velocity for as long a period of time. Then I want a wheel that has a little bit more moment of inertia, resistance to slowing down. Once I get it spinning, it's going to help maintain that moment of inertia, will help maintain that, in this case, angular velocity, which will translate to a linear velocity. So I want a wheel that has more moment of inertia if I'm trying to sustain a constant velocity. Greater resistance to change motion. But it's going to be harder to get this wheel spinning, and it's going to be harder to stop it as well. All right. So if I'm doing a course that's flat, based upon moment of inertia, I'm going to pick a wheel that has a little higher moment of inertia. If I'm doing a course that is hilly and has lots of changes and fluctuation, I may choose a wheel like this, where it has lower moment of inertia, less resistance to change angular velocity, and therefore maybe this will actually help me perform better in a race where there's going to be lots of fluctuations in velocity. All right, so we also need to know T equals I alpha. Well, going back to F equals MA, we need to figure out wheel selection based upon drag force. So drag force we know is 1/2 rho CdA V squared. CD is coefficient of drag and how well the air or the fluid moves over the object. And that's a function of how smooth the object is and the shape of the object. Okay, the smoother the object, the easier for the fluid to move over the object, the lower the coefficient of drag. A is the frontal area, or just that cross-sectional in terms of the direction of the flow of the fluid is hitting this portion of the wheel and then moving over. That frontal area is also going to influence drag force. And then rho is density of the fluid. V is the velocity of the fluid moving over the object, and we square that. But really, I'm interested in wheel selection based upon C, D, and A. So CD, this type of wheel that has this covering here, is going to reduce the coefficient of drag. It's going to reduce the drag resistance force. That's a good thing, right? This will help me go faster. Versus this wheel, which is also a rear wheel, which does not have any fairing on it. It doesn't have any covering here. So now as the fluid, the air moves over this wheel, it's going to hit all these spokes. And that's going to lower, it's going to make coefficient of drag worse. It's going to increase the drag resistance force because of the way that the fluid, the air, is hitting these spokes. All right, so this is a higher coefficient of drag than something like this. CD lower for the disc wheel, CD higher, coefficient of drag higher for traditional wheel. So why would I choose a traditional wheel? Well, I can beat this up. It's less expensive as the disc wheel. So I may train in something like this, but I may race in something like this. All right, so now there's this type of rear wheel, which has really a very shallow rim versus something like a rear wheel like I showed you before, like this one. This has a deeper rim. This will actually have a lower CD, coefficient of drag, than the other wheel. It also has a different profile in terms of frontal area, okay? And that's important in selecting a wheel as well, because CDA combined will influence drag force. But this wheel is actually going to be really helpful to have a lower drag resistance force because of a lower CD, and the frontal area is such that that fluid will hit the object at the leading edge, and it will also hit the object at the trailing edge of the wheel, at the trailing edge, as that fluid moves over the wheel. All right, so I may select this wheel for a rear wheel if I want to lower CD compared to my training wheel. So now, which of these two wheels would I select, and why would I select one over the other? Well, if it's a windy course, remember that wind can come at this wheel at all different angles, and it may hit this wheel at a side angle. Remember, we talked about how a drag force, aerodynamic drag force, can actually be a propelling force like a sailboat. That sailboat is catching that wind. That's a drag force acting on the sail and ultimately causing the boat to move forward. Well, the same thing can happen here to an advantage. This can act like a sail and help move the cyclist forward, but it can also push on the wheel to make it go in a direction that you're not intending to go in. So it can push here and maybe tilt the bike over in the wrong direction. All right, so on a windy course, you may not want to use a disc wheel. In fact, there's some courses that do not allow disc wheels to be used because the course is windy, and the winds can be very unpredictable, or they can be a crosswind. Whereas this is open, and so crosswind will have less of an impact on this type of wheel versus a disc wheel. But you still get the advantage of a deep dish that will help lower CD compared to a training wheel. So this is an excellent choice for a number of different courses. Okay, so now front wheel selection, we still talk about these same factors. And here are two front wheels. This one here and this one here. Now, there's also, I didn't bring one up, but I could also have brought up a front wheel that has this very shallow rim as well, but I've just got these two for comparison now. So why do I not put a disc on the front wheel? Well, when I'm riding outdoors especially, if I have this filled in with material and that crosswind comes along, it's going to have a tendency to turn the wheel. Right? It can create a torque about the axis of the fork and actually cause the wheel to turn. That can actually be disastrous if you're a cyclist and all of a sudden your front wheel starts to turn due to the wind. So it ends up being really hard to control and hard for the cyclist to go fast, or they end up wanting to slow down just to stay more in control. So a course that has lots of crosswinds, I would select a wheel that has a very shallow rim but it still has some aerodynamic benefit to it in terms of the shape of this portion of the wheel, because the air will move over it much nicer than a traditional rim wheel like this. So this will still help reduce drag resistance force, even though it's a shallower rim. This will actually reduce drag resistance force even more than the wheel I just showed you, because it's a deeper dish. It's going to have a lower CD. The air is going to be able to move over this wheel a little better than if this was a shallower rim. But I do sacrifice a little bit of control of the bike because it's a little deeper. So I really would still be a little bit careful. If I know I'm doing a course that has lots of crosswinds, I may actually want to choose a shallower rim than a deeper rim for up front. And then I have a little bit more confidence to be able to go faster without worrying too much that the wind will cause my, my front wheel to turn. All right, so those are some things to think about when we're doing wheel selection. That's the mechanics. Really two equations that we talked about here: sum of forces acting on the object are equal to the product of mass and acceleration, and then sum of torques equals I alpha. Using those two really help us sort of zero in on some decisions, why we would make a decision for selecting one wheel set over another. Okay, thanks everybody.